Okay, today we're going to talk about search algorithms. Overview for today, we're going to talk about linear search. We already did a little bit of practice with this with one of the earlier homeworks. Maybe I think maybe lab 9. Then we're going to talk about runtime analysis. So when we have different algorithms, how can we measure which algorithm performs better than the next? Then we're going to talk about another algorithm, binary search. And then finally, we'll finish off with the Wheel of Fortune competition. Any questions on anything before we get started? Okay. So linear search. Initially, we start off with initializing an array. So we put the data type, we put the name of the array. So in this case, we call it nums. What goes in the bracket here?
The number of items you need for your array.
Yep, the number of items, the size of the array. Then we put equals, and in the curly braces, we put that many elements in the array. So this array would initialize with the values 25, 9, and 18. Let's say we were looking for the target num equal to 18. Just in terms of English, how would we be able to tell if the target num is in the array?
You just look at it and then see which matches.
Okay. So as humans, well, okay, let's say even as humans it would be hard. Let's say we had like 1,000 elements. Okay. How then would we, because we can't look at all 1,000 and then just say, is it in or not? Like in one glance. How would we do it? How would we break it down?
Well, you asking like how?
Yeah, so if we had 1,000 elements, how would you be able to tell me if target num is in the array? What would you do? What would your process be?
We create a loop.
Yeah, so kind of a loop. And what are we doing each time?
Checking.
Yeah, like we're checking, is 18 equal to the 0th element? It's not. Then we check, is 18 equal to the 9th, like the first element? Is it equal to the second element? Right? So in terms of pseudocode, if we were to write out the pseudocode for this problem, we essentially say, like, for every element in the array, what are we trying to do?
Checking to see if it
Uh-huh.
is target num.
Yeah, so if like target num is equal to the element, right? Because we're going one element at a time. If the target num is equal to the element, then what do we know?
Target num is in the array.
Yeah, the target num is in array. So essentially we can return true. Okay, back to here. A lot of students, when they first did this lab problem, they would say else return false. What is the issue with this code here?
You don't really need the else because if it's true, or if it's not equal to the element, then it's just gonna get rid of those.
Yeah, but I guess even taking it a step further, in this example, we're essentially saying, so we're trying to check every element in the array, if it's equal to target num. So if we're saying if element equals target num, and we're checking is 25 equal to 18, we return true. Else, if we put else and we return false, with functions, when we return false, we immediately end the program. So once we return false, we wouldn't even check the other elements in the array. So in this pseudocode here, this else return false, it's only going to check the first element, and then it's either going to return true or it's going to return false, which is not what we want. So instead of the else here, at what point do we know? Let's say I was looking for the number 7. How would we know that 7 is not in the array?
After it's gone through all the numbers in the array.
Yeah, essentially if we've checked every element in the array and 7 was not equal to here, 7 was not equal to here, 7 was not equal to here, now we're outside the loop, we've checked every element, and if we never return true, then we know at that point it has to be false. The number is not in the array. So essentially outside of this for loop, after we've checked every element, we can return false. If at any point we had found the element, we would have returned true and we would have stopped searching. Does that make sense?
Yeah.
Okay. So this is essentially the pseudocode for linear search. For every element in the array, check if target num is equal to the element. If it is, return true. Otherwise, keep going through the loop. And once we exit the loop, then return false. So if we were to code this out in a function, first off, what would the return type be for this function?
bool?
Bool, because we're returning true or false. And then we need some data in order to know. We essentially need to know. What data do we need to know? So.
How many is in the array?
Yeah, so how many elements are in the array, so we know how many times to loop. That'll be like our size. What else do we need?
Index to count how many times.
Index, but we can create that inside the function because that will always start at 0. So we don't need to ask for that information. What else do we need? So we need the size of the array. We need the array itself, right? If we don't have the array, then we don't know what we're looking in.
Target number.
We need the target num to look for. Yeah. So we define it as double nums. When you're passing an array into a function, you don't need to put the size in here. You're just specifying like it's an array with the square brackets. Then we're saying we need to know the size of the array so we know how many things to check in the for loop. And then we need to know the number that we're looking for. I think defining functions is still a little bit hard for some students. I'm trying to give strategies for how we do it. It's like, try to think about what data we actually need to solve the problem. We don't need index here because we know index is going to start at 0, but we need the array, we need the size of the array, and we need to know what number we're looking for in order to tell if the number is in the array or not. Okay? So then in here, we need a for loop statement to get every element. So how can we set up our int index here?
For index equals 0.
Yep.
Index is less than the size.
Index is less than the size. Yep.
Index plus
Plus 1.
Cool. So you can either do index plus plus, which is the same thing as index plus equals 1, or even the same as index equals index plus 1. Okay? Cool. So this for loop syntax, you're going to see a ton with arrays. It helps us get every element in the array. What do we put in our if statement next?
if target num is equal to, or is it not equal to?
We'll do equal to, because in our pseudocode we were saying if the target num is equal to the element,
Okay.
then we're going to return true.
If target num is equal to index, then, or
So not index,
it'd be nums index.
num's index. So if we want to get every element in the array, we set up our for loop with index, and then we put the name of the array and index. That way we're saying like get the 0th element in nums, get the first element in nums, get the second element in nums. Are people good with that? Like this part is super common with arrays. We might print out this value, we might add this value to something, we might check this value against something, but generally the way we get every element in an array is using index and then doing the name of the array bracket index. Yep. Okay. So in this case we return true, and then at what point do we return false?
Once the for statement did that, our for loop's done.
Yeah, so our function ends here, our for loop ends here, so essentially right in between them, we would add return false. And this code is only 5 lines long, but it can be powerful, because even if nums is like 1,000,000 elements long, this code will be able to check each one of those 1,000,000 elements and be able to tell us if a number is in the array or not. Yep. All right, questions here? Okay. Hopefully some of this was review if you've done Lab 9. But now we're going to talk a little bit about runtime analysis and algorithms. So an algorithm, specific procedure for solving a computational problem. So in this class, algorithms that we've learned, this is kind of our first real main algorithm. Another algorithm we did is if we wanted to swap elements in an array, that's where we created the temp variable, and that was like a mini algorithm there. We're going to learn 3 more algorithms over these next 2 days. The point of algorithm analysis and creating algorithms is more for critical thinking. Like in the real world, someone has already created a function that can search an array for us, but it's helpful for us to build it ourselves just so we can see what's going on and understand different runtime efficiencies. So this is the definition of an algorithm. Runtime analysis essentially measures how efficient or quick an algorithm is. Can anyone guess why this might be important, to know how quick an algorithm is?
0.001 second.
Yeah, but why is it important to do this analysis?
Oh, why?
Like, why does it matter how fast an algorithm runs?
Because I don't know. So our computers are supposed to be fast.
You don't want slow, you don't want like your programs to run slow.
Yeah.
It's kind of like boring, standard for the consumer.
Yeah, it's like even though computers are fast, if your algorithm is bad, like a fast computer can't fix a bad algorithm, right? And so especially a lot of things, like could you imagine if you opened up Twitter and it took 2 minutes for all the tweets to load? You would be frustrated and you would probably stop using the app and you would go to a competitor instead.
Yeah.
Right? Same with Google search. Google search, you put something in the search box, within 60 milliseconds, it's able to index through millions of possible entries it could have returned and chooses the top 10 to show on the first page. That's all algorithm analysis. A lot of work and research has been done to figure out what's the fastest way to search a whole database of entries. So we're going to try to apply some runtime analysis to this linear search problem that we just did. And generally when we talk about algorithm runtimes, we talk about it in terms of best case, worst case, and average case. So let's first start with where would the best spot be for target num? So right now we're checking every element in the array and we return true as soon as we find the element. So what would be like the best case scenario for us?
Probably was the first one.
Yeah, if it's the very first item in the array, so essentially if it's in the 0th index, we just do one check and then we return true. Right, does that make sense? Okay, where would be the worst spot for target num to be? The last one. So essentially the n minus 1. So if we have like 100 elements and it's in the 99th index, that would be the worst case because we have to check all 100 elements before we figure out if it's true or false. Okay? So in the best case, how many if checks are done? One. How many checks are done in the worst case?
N minus 1.
Yeah, and so it'll essentially be n because we start at 0 index and we go up 10 minus 1, so there will be n checks. And then how many checks are done on average for this algorithm? So let's say we ran this function with like a bunch of different arrays. Target num could be anywhere in the array. On average, like the first time we run it, it could be in the first position. The next time it could be in the last position.
So
It-
50%.
Yeah, essentially like n over 2, right? Because if it could be anywhere in the array, it would average out to n over 2. So that would be the average case for this. Generally though, when we're talking about runtime analysis, we just look at the worst case. So I have a 5-minute or 4-minute video here.
Millions find a low-cost health plan at healthcare.gov so they can enjoy more visits and have less to worry about. Feel like a million and find your plan during open enrollment. Healthcare.gov is here for millions like you.
Today we're going to learn about Big O notation. So what is it? Big O notation is simplified analysis of an algorithm's efficiency. We cover a lot of algorithms on this channel, and we need a way to compare them and some idea of how long they'll take to run. Big O gives us an algorithm's complexity in terms of the input size, n.
This n is what we were talking about, like the number of elements in an array. We can symbolize that with like there's n elements generally.
It gives us a way to abstract the efficiency of our algorithms, or code, from the machines they run on. We don't care about the stats of the machine, rather we examine the basic computer steps of the code. We can use Big O to analyze both time and space. There are a couple ways to look at an algorithm's efficiency. We can examine worst case, best case, and average case. When we're talking Big O notation, we typically look at worst case. This isn't to say the others are unimportant, however. Let's talk about a few rules. First, Big O notation ignores constants. For example, if you have a function that has a running time of 5n, we say that it runs on the order of Big O of n. This is because as n gets large, the 5 no longer matters. In the same way, as n grows, certain terms dominate others. Here's a list, but I'll show you a visual on the next page. We ignore or drop low-order terms when they're dominated by high-order ones. Take a minute and study this chart. It can be found on bigocheatsheet.com, along with a handy guide on the Big O of various important algorithms.
This chart will make more sense after we learn some more algorithms to compare.
Let's run a few examples so you can see what I mean by basic computer steps. We'll start with constant time. Imagine we have the following line of code. This basic computer statement computes x, and notice it does not depend on the input size in any way. We say this is big O of 1, or constant time.
All right, wait, do people follow this? Like O of 1, because even if we had an array in this program that was like 100 elements or 1,000 elements, this particular line of code doesn't care about how big the array is. It's just doing like one statement. It's always going to run in the same amount of time. Does that make sense? Okay, so this is what we would call like a constant time line of code, O of 1.
What happens when we have a sequence of statements? Notice that all these are constant time. How do we compute big O for this block of code? We simply add each of their times, and we get 3 multiplied by big O of 1. But remember, we drop constants, so it's still big O of 1. Let's look at linear time. Suppose we have the following for loop that prints the numbers 0 to n. We know the print statement is big O of 1. This means the block of code is n times big O of 1. In other words, big O of n.
So I know this is Python code, but we could pretend the for loop is in C++. How many times is this for loop going to run?
In amount of time.
Yeah, so this is Python syntax, range 0 and n. It's going to print every number from 0 to n. And so in this problem, the big O notation becomes big O of n, because it depends. It's linear. If there's 1,000 elements, this code will run 1,000 times. So we say this is big O of n. It's not just constant time. It'll take different amounts of time based on how big n is.
Here's another sequence. The first line we know, again, is big O of 1, and the for loop is big O of n. The total time is the summation of these two, but remember we drop low order terms. When n gets large, the time it takes to compute y is meaningless, as the for loop.
So when it says like it drops the lower term,
Mhm.
so does that mean like say you're adding it, you just drop whichever one's smaller and then it'll be whatever you name?
Yeah, because essentially like if n is like 1,000,000, if n is equal to 1,000,000, this code will run like 1,000,001 times, like 1,000,000 for this for loop, 1 time for this one. So this one like really doesn't matter.
So like there was like, I don't know, I don't think I'm remembering it right, so I think there was like an equation that had a bunch of them.
Yeah, so like a bunch of O of 1s and it said like 3 times O of 1. Yeah, in that case we can also, essentially we're just trying to get it to one like O of something.
So the O1 doesn't change at all.
O of 1 is just meaning like it just runs one time regardless of how many times the loop or like array, how big the array is. Yeah.
And then O(n) just runs until that n number.
Yeah.
Okay.
So this is what we call like, this code is going to take way longer than this code here.
Okay.
So we just only factor the part that takes the most amount of time.
Runtime. Finally, let's look at quadratic time. I think you can see that the print statement will be executed n times n.
Wait, okay, so how many times is this outer loop going to run?
N times.
N times? How many times is this inner loop going to run?
1 time.
It's going to run like n times n times. If we have nested loops,
Right.
the inner loop is going to run the outer loop amount of times times the inner loop amount of times. So n times n. So this code, print x times y, is going to run n squared times. So our big O notation
Which gives
here,
us big O of n squared.
what do you think is faster, O of n or O of n squared?
Oh,
O of n will be faster. Like O of n will run less times than O of n squared.
Right.
Yeah. And this is like bad. If it's an exponential, like if n is just 100, O of n will result in 100 times. O of n squared is going to be 100 times 100, which is like, yeah, a lot longer and a lot slower essentially.
Let's do 2 more examples covering everything we've talked about. Say we have the following block of code.
Okay. So what is this first line? What O is that going to be?
Oh, one.
O of 1, because it's constant. It doesn't matter on n. Then this for loop here. That's going to be O of n. And then this nested loop here. O of n squared. So what's like the biggest term? Yeah, so we can end up dropping the others.
What is its total runtime? Well, we know the runtime for each of these, so the total runtime is simply the max of the 3.
So O
The
of n
nested
squared
for
for
loop
this.
dominates here, so we get big O of n squared. How about this if-else statement?
Okay. Cool. So using what we learned here, going back to our linear search code, in the worst case, so when we're doing big O notation, we're looking at the worst case. And how many times, what was our worst case scenario for linear search? Where is the element going to be located?
N minus 1.
Yeah, at the very end of the array. So how many times is our loop going to run?
For this one,
If it, in the worst case, how many times will this run?
uh,
Yeah, it'll run n times. So like if the size is equal to n, if there's n elements in this array, the worst case this is going to run n times. So what is our big O notation?
O of n.
Yeah, so we'd have O of n. Questions here?
I had did everything in there, but I didn't have Google in front of the function. I saw it, so I don't know what it was. I remember. Okay.
Yeah, because the return type we're going to return true or false. Yep,
Okay.
got it there. Cool. Okay. Questions here before we move to binary search? Okay, so this algorithm to find a number runs an O of n time. Now we're going to see if we can do it better. If we can try to come up with an algorithm that actually runs faster than O of n time. So in the worst case, we don't have to check every element. So let's say I told you I have a number between 1 and 100. Let me think of a number. Okay. I got my number. And I'm going to tell you if your guess is high or low. So can someone take the first guess at what my number is?
17.
Okay, I've heard. Okay, so we'll go with 12. My number is higher than 12. 48, higher than 48.
70.
70, higher than 70.
92.
Less than 92. 84, higher than 84.
87.
Higher than 87.
90.
Less than 90.
89.
Less than 89.
88.
88. Okay. So notice after we guessed 12, what was our next guess? I think it was 48. Why didn't we just guess 13, even though 13 is already higher?
Because you want to eliminate the most amount of numbers as
Yeah. Like we could have done this with a linear search. We could have said, is your number 1? Is it 2? Is it 3? Is it 4? And gone all the way up to 88. The ideal one here, the ideal start wasn't 12. What would the ideal start have been here? 50. How did we get 50?
It's right in the middle.
Yeah, we're trying to essentially, every time we make a guess, we want to split our search in half. So we guess 50. If it's greater than 50, what would the next ideal guess be?
75.
75. So each time, and let's say it was less than 75, we keep trying to shrink our search area, right? So if we had an array, how can we define a double array? What goes first? Double, let's call it nums. And let's say we have 7 elements. So what would go in here?
7.
Okay. So 7, and then if we want to initialize it, let's say our numbers were like 2, 5, 12, 22, 31. How many is that? 1, 2, 3, 4, 5, 84, 99. Okay? And then we have an array that holds those values. Let me write them out in red. Actually, we'll do blue. Okay. So our array then would look like. Our array would look like this. 2, 5, 12, 22, 31, 84, 99. Okay? Let me also just make sure I didn't miss anything. Okay, so binary search algorithm, we're going to keep trying to divide the search area by half. Okay, so let's say the target num we were looking for is, let's go with 84. Okay, so 84 is the number we're looking for. We have our different indexes. So index 0, this one's going to be index 6. What number should we search first to check if target num is equal to? Yeah, this 22, because then we have 3 numbers on our left, and we'll have 3 numbers on our right. If the target num is equal to 22, what do we do? We return true, and we stop. If it's less than 22, which side of the array do we want to search? If target num is less than 22, we'll search the left side. And if target num is greater than 22, then we're going to search the right side. So each time, we're going to find the middle index, and then figure out if we search the left side, if we're done, or if we search the right side. Okay? So how can we get the middle index? So let's say we have like a start index variable. When the problem starts, what is our start index going to be equal to?
0.
And
Yeah. Like, yeah, we'll start it off at 0. And then our end index is going to be equal to, yeah, which is like the size minus 1. Okay? So that's where they start. And then we're going to create an extra middle index. And middle index is where we're going to start our search. So how can we calculate middle index?
End index minus start index divided by 2.
Yes. And
Oh wait,
yes. Or I'm trying to see if we add it. You might need to add them together.
Add to the start index.
Yeah, because later when start index moves over, we want to add them. Yeah, we do want to add them together and then divide. So it's going to be start plus end divided by 2. Okay? So when this problem starts, it's going to be 6 plus 0 divided by 2. It's going to be equal to 3. So this 3 is our middle. This is our start. This is our end. Okay? And then we're going to check. If target num is equal to, and we'll call this array like nums, what do we put in the bracket here? Nums of what?
nums of middle index.
Middle index. I'm just going to do m for short, so that's middle index. Then we return true. Alright, else if, sorry, my handwriting sucks. If target num is greater than nums of middle index, where do we know that target num is located? If it's greater than whatever's in the middle index.
We're on the right side.
It's going to be on the right side. So now we need to update some variables.
It'll be middle index plus 1, right? Because don't you have to move up 1?
Yeah, but we don't want to just move middle index over 1. We essentially, so we're trying to shrink the array. So the only 3 numbers we care about in this array now, because we know it's not 22, and we know it's nothing to the left, we know the start of our array now is at 31.
So it'll be start index is equal to middle index.
Yes, so this start index is going to move here to middle index plus 1. So start, I know it's just that everyone can see it. Start is going to be equal to middle plus 1. Okay? So now start is equal to 4, end is equal to 6, and when we calculate middle,
So 84.
it's going to be 4 plus 6 divided by 2, it's going to be 5. So middle is going to get updated there. Okay? It's a little bit slow for me to write it all out on the whiteboard, so we'll do it in the visualizer. Okay. Everyone can see okay? All right, so let's define this function. What is the return type going to be? Bool, because we're returning true or false. We'll call it binary search. What information do we need?
Of the double nums,
Yep.
size, array number.
Yep, we need the array that we're looking for. We need the size. and we need the target num that we're looking for. So it looks very similar setup to linear search, right? Both searches take the same data. The difference is how we're going to try to find the number, okay? So in here, we're going to create our start index. So int start index equals 0. Int end index, what is this going to be equal to?
Size minus 1.
Size minus 1. Middle index.
Start index plus end
Mhm.
index divided by 2.
Yeah. And so actually, so we're going to do, sorry, we'll do this in the for loop. So essentially, while, at what point, we'll come back and fill in the while, because that part's probably the hardest part to figure out in this problem. But we want to keep making the array smaller and smaller. And so we said here, we'll create int middle index. Okay, so middle index is equal to, what is it equal to?
Start index plus end index divided
All right, what's going to be wrong with this line of code?
You gotta put start plus end.
Yeah, so division takes priority, so it divide this by 2 and then add it to start index, where really we want to add these two together first and then divide by 2. Okay? So that's our middle index. And now we have our if, else, if, else. So let's do the easiest one first. If target num is equal to, and what are we trying to check if it's equal to?
Now,
Num's middle index. Then what do we want to do?
return true.
Return true. And remember with functions, as soon as we return something, the function immediately ends. So we would stop searching in this case. Else if target num is greater than num's middle index. So we know that the array, like we only want to search the right side of the array. So what can we do to the start index?
Start equals 0 plus first one.
Yeah. Okay. Else, we know that target num is less than the middle index. So instead of, now if we were searching this side,
Minus 1.
yeah, but what's minus 1?
Start index,
If we do start minus 1, start is going to be a negative 1.
middle index.
We don't want to move middle 1 till later, because we're always doing middle with start plus n divided by 2.
It would be end index is equal to middle minus 1.
This end is going to move here to middle minus 1. Exactly. Because now our start is here and our end is here. Right? So in this case, we're really moving the end index. So end index is equal to middle minus 1. Questions here? Should we run it? See if it works? All right, well, I guess we got to call the function.
What's the condition though, in the while loop?
Oh, good point. So let's say we were looking for, okay, so let's run this code, but let's say our target num is 85. So 85 is the number we're looking for.
Well, target node is not equal to 85.
Okay, so we'll check it. So start index 0, end index. Okay, so our array will work for this. Value of middle index is going to be equal to 3 to start. And so we check. Does target num equal nums of middle index? Does 85 equal 22?
No.
Is 85 greater than 22?
Yes.
So what happens to the start index?
It is, it's equal to middle plus 1.
Okay, so start is going to be equal to 4. Okay, now we come back to the start of our while loop and we update middle index. So what's the value of middle now going to be?
Oh, is it 5?
Yeah, middle's going to be 5.
Oh, okay.
Okay, so middle is 5. And we check, is 85 equal to 84?
No.
Is it greater than 84?
Yes.
Okay, so what do we do to start index?
Move it to 5.
5 plus 1, right? Start is equal to middle plus 1. So start is going to be equal to 6. And now we do the loop again. So middle is going to be equal to 6 plus 6 divided by 2. So middle is going to be 6. So all of them are at 6 now. And we check, does 85 equal middle of 6? No. So then, and it's less than it, right? So what happens to the, we come into this case. What value does end index take? Yeah, So end is going to be 6 minus 1. And now we have this weird thing where like our end is less than our start. And that, like, it doesn't make sense for our end to be less than our start. So that's essentially our while loop condition. If that ever happens, then we know the number is not in the array. So here our condition would be like while essentially while the start index is greater than or equal to the end index. Kind of hard to fully visualize it, but if the start and end ever switch places completely, then it means we couldn't find the element in the array. Yeah. So I know it's a little bit tough to visualize. Oh. A little bit harder to visualize it on the whiteboard. We'll do it once in here. Okay, binary search. Double nums 7 equals nums 7 and the number we're looking for. Let's look for the number 3. Unexpected if target num. Oh, missing this. Missed it everywhere. Okay. Cool. So when we run this code, we call binary search. Okay. So start index equal to 0, end index equal to 6, and we check, does start index, sorry, it should be, well, start index is less than or equal to end index. Then we want to run this. Okay. So is 0 less than or equal to 6? Yes. So middle index becomes what value? 3. So then we check if target num, which is 3, is that equal to nums of 3? So is 3 equal to 4? No. Is 3 greater than 4? No. So then what happens to the end index? Yeah, so it's going to be 3 minus 1 is 2. So now if you see our start index is 0, our end index is 2. So we've shrunk the size of the problem in half. We know it's between those two. And so when we can keep running, middle index now is going to be half of that. So middle index is 1. We check, it's greater than, so now we increase the start index. So now we know it's between like these two values here. And essentially the takeaway from this algorithm is we keep making it smaller and smaller. Okay? So if we were to quickly do the runtime analysis for this, how many if checks are done in the best case? 1, the number ends up being right in the middle of the array. How many are done in the worst case? It's no longer n because we're dividing it in half each time. Yeah, so it's this new, we haven't really learned it, it's called log of n. Essentially what log of n is you take whatever, so it's like log of 2 is 1 because, okay, log of 8 is 3 because 2 to the third is 8. 2 to the 4 is 16. 2 to the 5 is 32. The other way of looking at this is every time we divide the problem in half. So if we had 16 elements in our array, we'd only have to do 4 checks. Because if we have 16 elements, we divide the search area in half to get to 8. Then we divide the search area in half to get to 4. Then we divide in half to get to 2. Then we've essentially found it. So we keep dividing the problem in half. So this is what we call a log of n algorithm. And log of n is faster than n. So you'll see if we had 128 elements in the array, we would only have to do 7 checks in the worst case, which is super powerful. If we had 256 elements, we'd only have to do 8 checks total to find this number. So the runtime analysis, best case for linear search, both of them are O of 1 time. But when we're doing runtime analysis, best case doesn't really matter. Because how often is the best case going to come? Like 1 in n times. What we care about most is the worst case. when we're talking about runtime and how good an algorithm is. So linear search, if we had 128 elements, we would have to do 128 checks in the worst case. With binary search, we would only have to do 7 checks in the worst case. Can anyone guess why we wouldn't always do binary search though? What is the assumption we had in binary search?
That is divisible by 2.
Yeah, partially. We could have done it even if it wasn't exactly. What do you know about the numbers in terms of their ordering? It has to be sorted. It has to be sorted for binary search to work. Linear search works even if it's not sorted, because we're just checking each element by itself. Binary search requires it to be sorted. So if you have a sorted array, binary search is better. If you don't have a sorted array, then you have to use linear search. Okay? All right, questions there? Okay, cool. Let's go into Wheel of Fortune cash. Okay. All right. Cool. All right, if you finished the 4 assignments, raise your hand and I'll put your name down. All right. Omar, Kadar, Sandro. Okay. Everyone good? Yeah. It was like homework 7, homework 8, lab 7, lab 9. Okay. Cool. Okay. Cool. So I'm gonna pick 3 names from here. Boom, bada boom. Okay. John for 1. Remove. All right. Ooh. Kedar. All right. And last one. And Isaiah. All right. Cool. Okay. And then I'll have you 3 come up to the middle here. You're each going to have a marker. All right, Isaiah, John, Kadar. Once you know the answer, say buzz, hold up your marker, and then I'll pause the video, and whoever buzzed first will get a chance to answer. You only get 1 guess, so if you get it wrong, you're out for the rest of the round. We'll do 1 practice puzzle so that you all understand how it's going to work.
Customize and save the reviews.
Okay. All right. So this one's just the practice round. All right. I just need to be able to see you all. Okay? Cool. Yes.
This is worth $2,000, and the category
Again,
is
this one's the practice one, but treat it like the real thing.
Buzz.
Okay.
The gold rush.
Yes, the gold rush. All right, just make sure you buzz before you say it. Okay. Cool. So now the actual one. For $100. Everyone ready?
Wait. We're
Yeah.
not guessing any letters, we're just guessing the word.
So the letters are going to randomly appear. Once you know the answer, you buzz. I'll pause the video. And then, all right.
Food and drink is the category. Here's the first of our 3 puzzles.
Food and drink.
Buzz.
Buzz.
Cotton candy.
Cotton candy. Let's see. All right. $100 here, $20 here. I will bring in the money on Monday because I brought it in on Wednesday, and then I think someone went into my office and took it, so that was a little bit sad. But hopefully whoever took it actually needed it. I shouldn't have left it over these last couple days, but I will bring it on Monday. So $100 here and then $20 here. Thanks everyone for participating. Make sure you come in on Monday to collect because I don't want to leave the money unguarded again.
Cotton candy from.
Like 3 seconds.
I don't know.
Well done, well done. Thank you. All right, cool. Homework 9 due on Monday. Lab 10 today at 4 p.m.
I'm thinking one time.
I seen hella holes.
Yep, take care. Yep, take care, take care.
That was good.
Yep.
Is Dr. Washington today?
I believe so. Yeah. Okay, I'll get your attendance. Yep.
Also, are we gonna go over this again next week sometime?
The like search algorithm stuff. We're gonna do new algorithms, but we'll recap this at the beginning. Yeah.
In lab or in class?
Homework will be coding out these algorithms. Lecture will go over it one more time.
Okay. Cool.